I just wanted to talk about the property of continuity and show how that it's actually a much more special property than maybe we give it credit for. So I'm going to introduce a function that has no limits anywhere. Seems a little strange because all the functions that you've seen in high school have either been continuous or only discontinuous on a discrete or even finite set. So you've seen functions that were maybe wave, sinusoidal, or some kind of polynomial, or maybe just a straight line. All these functions are nice and continuous everywhere. They don't behave, exhibit any strange behaviors. But we've also seen functions that maybe do some stranger things. So maybe they have an infinite limit and maybe a hole somewhere, and or maybe there was just a kind of a jump discontinuity somewhere. So something like that, something like that. So we've seen all these different kinds of of discontinuities rather. So my question for you to ponder here is, what would it mean for a function to be discontinuous everywhere? That seemed like a bold ask, because even here, even in these graphs, the function is continuous everywhere, almost. So basically, anywhere that there isn't a hole or isn't a jump, the function is nice and continuous there. So this seems like a tough ask for it to be discontinuous everywhere. We need some kind of jump to happen at every point. So something like this to happen at every point. How can we even make sense of that? Well, let's talk about this special function. Some people call this the Dirichlet function or the indicator function of the rationals. And the function is defined as follows. It's going to take the value 1 if its input is a rational number, and it's going to take the value 0 if its input is an irrational number. So let's see if we can get a feel for how this looks. Maybe we could try to graph it. Okay, so let's consider the unit interval. I know that 1 and 0 are nice. So let's do it in blue maybe here. So 1 and 0 are both rational numbers. So I'm going to put a dot up there for at 1 for those inputs. Okay, but we can also look at stuff like a half and 3/4 and a quarter. And all of these are nice rational numbers, so I'm going to also include some blue dots up there for those. Okay, but we don't just have rational numbers in here. What about something like the square root of 2 over 2? Or maybe something like pi over 4? Those are nice irrationals. So they'll have dots down at 0. But yeah, this process is going to take too long. We're going to get a lot of points up here for every rational number, and we're also going to get a lot of points down here. In fact, we're going to get so many that I would prefer to just draw the graph like two solid lines with many holes. So this is my function f of x. And this function truly jumps at every single point. This function has no limit anywhere. Jumps at every point. Very strange. This isn't the usual kind of function that you deal with, that you've seen in high school, but it does open up a different lens on functions that you can consider. So if you aren't convinced by this kind of picture argument, I'm going to run through a quick epsilon delta argument. So I'm going to use the definition of limit to show that this function cannot have a limit anywhere. So I'm going to use the fact that in any open interval, there are rational numbers and irrational numbers. So in any open set of the real line, there are rationals and irrationals. And I'm going to fix an epsilon to be a half, let's say. I could pick it to be 1. I could pick it to be a quarter. It doesn't really matter. And I'm going to fix delta. Actually, let's fix just any real number a. And let's let delta be any positive real number. Then in the interval, a to a plus delta, I'm going to pick I'm going to fix x to be a rational number in that interval and y to be an irrational number in that interval. So this is from our fact above. But then that means that x minus a and y minus a are less than delta. But f of x minus f of y is just 1 minus 0. So that's using the definition of our function up here. If our input is rational, then its output is 1. If our input is irrational, then its output is 0. And x is rational and y is irrational. So that's 1, and that's going to be greater than a half, which is epsilon. So I let delta be arbitrary. It could be arbitrarily small interval around to the right of a, I guess in this case. Same argument works for the interval a minus delta to a, but there's simply no way that I can ever make my function values get close enough together for me to possibly define a limit. A was arbitrary, delta was arbitrary. Uh, that means that there's no function limit anywhere. Now, this might seem like a bit of a contrived function example, and in a sense it is, but I would argue, and have good reason for this, that continuity is a bit of a rare property. It's almost hard to find if you look at the set of all functions. A very strong condition on a function. And this function, if I had a favorite function, this function would be my favorite function because it offers a sort of portal to a new way of thinking about functions. And it breaks a lot of your intuitions that you've got from high school.